And in the last class we were talking about the ionic crystals, where you saw that the local stacking depends upon the relative sizes of the two ions which are involved, and then discussing number of them with coordination 4, 6 and 8, we went on to see SiO2, which in its crystalline form we looked at quartz and its applications. Then we saw that usually SiO2, when it is molten and is allowed to solidify, doesn't become crystalline. Usually it is non-crystalline in nature, and that gives us the glasses, the window panes, the wind screens, all these viewing windows which are made of silicate glasses are based on that, with some impurities which are called modifiers. These are all oxides. They go and break the tetrahedral network and make the viscosity of the glass lower, and thereby lowering the glass transition temperature or the softening temperature of the glass. Continuing with the non-crystalline structures, we move on to look at other non-crystalline structures which are polymers, particularly the organic polymers. Well, as you have read in school, polymers means many units. Poly word means many and mer means a unit. So the many units means many mers are there, could be in the range of 10,000 to 100,000 mers in one molecule which we are now looking at. That's why it is called a polymer. Polymers have been classified in number of ways. One of the classifications is on the basis of the arrangement of monomers in space. If it is all along the line, so these are all monomers shown here, and these monomers are joined like this along this line which is curved. This is a curvilinear line. This is called a linear polymer or a chain polymer. Then another is a network polymer, where the monomers are attached to other monomers in all three dimensions. So for example, this one is attached to this one is attached to this and that, maybe somewhere else, attached to this one, attached here, attached there, and so on and so forth. They form a network. And they are in different planes and they are forming a network in 3 dimensions. So once they form a network like this in 3 dimensions, the whole thing is a one molecule. Whole volume becomes one single molecule, whatever be the size of this molecule. These are called the network polymers. So on the basis of this arrangement of these monomers in space, they are either linear or network polymers. What you notice is, I have shown here one molecule, here also this is one single molecule, but there can be more than one molecule in here, but there cannot be another molecule here. The whole volume is one single molecule. Well, the other classification on the basis of their behavior to the temperature, one of them is called thermoplast. As the name implies, thermo means you heat, plast, it becomes more pliable, it becomes soft. So if you heat a material, it becomes soft. These are called thermoplasts. Usually on their structure, they are long chain molecules, and between the molecules, the long chain, there are only secondary bonds which are van der Waals forces. All these, as I said, soften on heating and harden on cooling. They become more rigid. Well, you use number of such plastics, thermoplastics. Like you might have seen some of their file folders. Their covers are very soft in summer and they become quite rigid in winter. As you cool, they harden. As the temperature rises, they soften. And in softened state, where they can be below their melting point, of course, it's possible for us to mold them and extrude them and give them the shape we want. So the processing becomes very easy for such materials. Giving them the shape, desirable shape, is quite simple. Some of the examples of these materials which you use: polyethylene, we simply call it sometimes polythene. Polythene carrier bags you usually use. You have the polythene suitcases, containers made of polythene. Well, pipes, tubes made of polythene. Then PVC, polyvinyl chloride. You have the insulations, sheets made of polyvinyl chloride. You have also tubings made of polyvinyl chloride. Gramophone records can also be made of polyvinyl chloride. Then we have PTFE, which also falls in this category. The market is called Teflon, polytetrafluoroethylene. This is one material which has a very high softening temperature, and it usually doesn't stick to anything. So your non-stick wares, cooking wares, you are having the coating of PTFE on them. And because of the non-stick quality, they are, to engineers, they also provide good lubrication as bearings. Polypropylene is another some such material which is long chain polymer and thermoplast. Well, you make these days the dashboards of your automobiles, the bumpers of your automobiles of polypropylene. Well, sports wears are also made of polypropylene these days. Then we have polymethyl methacrylate, which is also called the plexiglass, or usually your wristwatches, you have the windows and these, they are made of this plastic material which is called plexiglass. It is very transparent material and a substitute for the silicate glasses. It is soft, pliable, and this is polymethyl methacrylate. So these are some of the thermoplastics which are there. Then on this similar behavior, on the basis of heat, we find another material which are thermosets. Structure wise, these are usually three-dimensional network of primary bonds, like what I showed, the network polymers. And as the name thermosets, you heat, thermo means you heat, it sets means it hardens. So as we heat, it hardens. And the why it hardens is if there is any leftover process of polymerization that goes to completion with the available thermal energy by heating, and these are becomes a complete molecule, single molecule, three-dimensional network. Similarly, if theirs are once made as a single molecule, you give it a shape, whatever shape you give, or sometimes the process of polymerization is made through a chemical reaction. Then once it is given a shape, it forms that shape. It is, before it can melt or even on heating, it degrades, combines with the atmospheric oxygen and degrades. It is not possible for it to melt so easily because they are all primary bonds, sp3 bonds, they do not break so easily. So it does not soften on heating, rather even before it can melt, it degrades. Must be one more. Somewhere. left out one slide. Yeah. Even before they can melt, they degrade due to their reaction with the atmospheric oxygen. It's a reaction. You must have seen, see, we have the using the bakelite is one such material, and making the switches. When you put switch off and on, there is usually sparking taking place. As a result, sometimes the contact can be loose and there could be constant sparking going on. If that is happening, you hear, means you smell sometimes something, and it's a burning of bakelite. So with the heat, instead of softening, it starts burning, you know. That's it, degrading. It's combining with the atmospheric oxygen and burning off. So that's the kind of thing that happens in thermosets. They do not, it's not possible for them, once you have given them the shape, it's not possible for you to join them by heating process, which you could have done with the thermoplasts. Thermoplast, let's say PVC, it let's say breaks. You can simply put the broken pieces together, heat it a bit, and just allow them to come together for a while, and this will, all the chains will intermingle again, it will become a one piece. It's possible for you to do treatment like that to this, or you can give it a reshape it, but you cannot reshape these materials. Bakelite, melamine, araldite, aeropol, these are some of the network polymers which are thermosets, and these cannot be reshaped. When it is sold, these materials are sold in the market as a raw material, they have to be sold as partially polymerized materials. If they are fully polymerized, you cannot do anything with them. So in partially polymerized chips which are available, you put them in a cavity of a die, press it and heat it. During the heating process, whatever is the polymerization process incomplete, that goes to completion because of this heat. Under the pressure, you keep it until you take the shape of the die, and this is final product formed, and that final product is one single molecule, right? So therefore, it's not possible by heating process to join these back. You cannot remold them. If they are broken, they are useless. You can have to simply throw them. You cannot reuse it. Now, on the basis of the arrangement of the long chains in space, the long chain polymers we will talk about today, because these are the ones which can, as engineering material, you can use them more quite and reuse them also. Plastics in which chains are placed zigzag in three-dimensional space, and between the chains there are only secondary forces, these van der Waals forces. There are no other kinds of bonds between them, only van der Waals forces, and primary bonds are all along the length of the chain, and chains are placed quite zigzag in the three-dimensional volume. These are the plastics. Like some of them are named already. Thermoplast, which I talked about. The fibers, another long chain polymer, but here each chain is arranged parallel to the other. Though they may not be of the same length, they may be of different lengths, but they are arranged parallel to each other, and they are held parallel because of the hydrogen bridges between them at few places, and they maintain their length because of these hydrogen bridges, which come at regular interval. There is some kind of a periodicity in that, and as a result they remain parallel to each other, and these fibers are very strong in the direction of the axis of the fiber, because in the axis of the fiber, when you try to pull, you are pulling only the primary bonds. Only when you go across, you are pulling the secondary bonds. So along the axis of the fiber, they are very, very strong. So that's, you have nylon, you have cotton, you have Dacron. All these things are fibers, the natural fiber like jute, you can have the cotton is also a natural fiber. Well, we have the third category of long chains, which are elastomers. Really speaking, they are long chains, but in between we have a few cross links like this between chains, various chains like that. These cross links are primary bonds between the chains. That means it is something like you have a long chain, but in places it is trying to become network. So it is between the two. It's not, if I do the cross linking at all places, then it will be absolutely a network polymer. But it's only few places these cross links are there, and as a result, and the chains are quite coiled, not really zigzag, they are coiled, and these materials, when they are stretched, they stretch 300%, 400% of their original length, and when release the force, they come back to their original shape and size. It is different from, the behavior is very different from the other two. If you are able to stretch this, you can try this, you can cut a strip from a polythene bag and stretch that strip, you will be able to stretch it, but it will not come back. Take a piece of rubber band, you stretch it, it comes back. And this coiling which is there on stretching is getting uncoiled, and these primary links are making it come back, that we will see in details when we come to elastomers. But these are the three basic arrangement of chains in space in as far as structure is concerned in long chain polymers, and because of the arrangement, these are called plastics, they are called fibers, and these are called elastomers, okay, because they behave in a rubber like manner. We'll call them elastomers. Now we shall look at the plastics first, then we'll go to look at the fibers, some of the fibers. Easy for us to look at the plastics with the help of a monomer of ethylene, C2H4. There is one double bond and this is one molecule of ethylene. When we polymerize this double bond saturates, becomes a single bond, but provides a single bond here and a single bond there, to which I can connect another monomer there, I can connect another monomer here, and this chain can extend on both sides. Once that happens, I refer to this as polythene or polyethylene. Otherwise, this molecule is an ethylene molecule, which is a monomer, right? This is what I mean by polymerization, that this double bond is saturated, provides the links on both sides, and those links are connected to other monomers in the same fashion. That's what is a polymerization process. Well, this is what is a polyethylene molecule, chain rather. This is one monomer, that's another monomer, third monomer, fourth monomer, and so on and so forth, and these monomers are connected here like this. So this is all the carbons I am showing as black ones or the grey ones, and these blue ones are the hydrogens. On this chain, how many such monomers are there is called the degree of polymerization of the chain. So if I know the molecular weight of the chain molecule, divided by the molecular weight of the monomer, it becomes the degree of polymerization. In other words, it is equal to the number of monomers in the chain. But in the solid, no two chains are of the same length. No two chains have the same degree of polymerization. Therefore, we work usually on terms of the averages or the weighted averages to find out this degree of polymerization or average degree of polymerization. Yes, please.
This will be equal to number of monomers in the chain, and there will be no using of such molecule NH3H, the small molecule from the when the monomer condenses to form a polymer. They are two options, like either like ethylene forming polyethylene, like amide polyamide forms in which the NH3 or H2 molecules are loose.
Yeah.
So in that case, it will not be equal to the number of monomers in the chain.
There is a difference between the, well, I am not talking about the processes of forming polymers. In school you have already of course studied there is an addition polymerization and there is a condensation polymerization. Here we are referring to the additions. What I have talked about polyethylene is only addition. Okay. So this we are referring to the addition, and therefore it is the molecular weight of the chain molecule and molecular weight of the monomer will work in this case. When you talk about the condensation polymerization, we will normally be forming the network polymers, right? Well, this is actually the one monomer unit, and on the basis of which I am going to talk about other plastics as well. Two carbons, 1 and 2, and then this is a one side group, second side group, third side group and the fourth side group. Numbers 1, 2, 3, 4 you can make in any order. 1, 2, 3, 4, these are the four side groups which are hydrogen in the case of polyethylene, and these are the two carbons. So for all others, what I do is I call this as side group R1, side group R2, side group R3, side group R4, and see what different plastics I am able to get by changing these R1, R2, R3 and R4. For polyethylene, as we are talking about, R1, R2, R3, R4 are all hydrogen side groups. That is what I have showed you, and that is on the basis of which we are going to talk about the others. And I already said that we can use this material for containers, carrier bags, etc. That is where we are making use of it. Even the suitcases you can make out of it. Polyvinyl chloride is the next one which we shall look at. Where the three side groups are hydrogen, hydrogen and hydrogen, R1, R2, R3. Fourth one is a chlorine atom which is a little bigger one as compared to hydrogen, and this forms again a chain molecule. It is used, well, it's a rigid material though, and can be used for your pipings, sheets or the gramophone records, etc. Insulation is the greater use for the PVC in electrical insulation of the wires. Well, this is made more pliable by addition, we make some additions of either copolymers to it, or we add some plasticizers to make it pliable and soft. Usually it is a rigid material in the pure form. And see the molecule R1, R2, R3 are hydrogen, and the fourth one is the chlorine. It's a much bigger one, bigger than carbon, and that repeats, and these are the repeating can be added here and there. And notice that one important thing, for carbon these four bonds which are extended, these are sp3 bonds and they are not in a plane. You can see that it starts here, goes outwards, comes in front, goes back, this also is going backwards. So these 4 bonds are sp3 bonds, tetrahedral bonds. You see the same thing here, the tetrahedral bonds. Alright. Next one should be polypropylene. Next one should be polypropylene, and polypropylene has 3 side groups, hydrogen, hydrogen and hydrogen, and the 4th side group is a big one. You see, it is CH3, it's a bigger one, and the arrangement in the space is going to be a little more ticklish because they remain zigzag completely, and this is polypropylene. It's a material used, as I said, in the dashboards. Polypropylene is a material used as bumpers of the cars. Polypropylene is also used in making buckets or the plastic wares you may use. And these days, polypropylene, we draw the fibers, we spin the fibers out. The melt is made to drop on a rotating disc, and fine fibers of the polypropylene are taken out. Then it is converted into staples, and you can make a thread out of it, and you make the sports wear. Polypropylene does not absorb water at all, but in the capillaries formed between the fibers, a lot of water can be the surface tension, and that's why these sportswear can absorb all your sweat when you are working or you are running or you are playing. You sweat a lot, and all this sweat can be absorbed by them, and when you jerk it, it becomes absolutely dry. Just simply by jerking or shaking, you can remove all the water from between the fibers because it is held by surface tension alone. That's why toweling material is also very good. Toweling material, soft toweling material made out of this, it can absorb a lot of water, but it can become very dry very soon. Next is polymethyl methacrylate. 2 side groups are hydrogen. Third one is CH3, just I showed you, and the 4th one is COOCH3, still bigger group. This is also called the plexiglass, and I told you that window panes or the transparent windows can be made out of. This material is a very transparent material. These are the 1 and 2 side group. Third one is CH3, 4th one is COOCH3, oxygen atoms this side. Okay. This is carbon, and this is again hydrogen CH3. Everywhere you see carbon is having tetrahedral bonds. This is a double bond with oxygen, but that's a single bond there. And this is a window material. The next one is polystyrene, where 3 side groups are again hydrogen. The 4th one is a benzene ring. This polystyrene is a very hard and transparent material, but in that form we don't use it. We use it in the form of foam mostly, which is called styrofoam. And styrofoam is what is used for heat and thermal insulation. It is used in packaging or as a thermocol, That's what is the styrofoam is. And if you look at its unit, monomeric unit in polymer, this is 1, 2, third, 3 hydrogen side groups. The 4th one is a benzene ring. 6 of the carbons, these double bonds, which of course will be rotating, and these are the hydrogens connected. Important thing to be seen is all connections are through sp3 bonds. Polytetrafluoroethylene is the next one. As engineers, as I already told you, we use it for all the side groups are fluorine, and we use it, its non-stick quality in bearings. We make the sliding bearings, we make the rotating bearings. Journals can be rotating, steel journal can be rotating in a bearing made of tetrafluoroethylene, that is Teflon. It will keep working with very small friction. It provides a coefficient of friction with steel less than 0.5%. That is of the order of 0.005 coefficient of friction, or between 0.005 and 0.01. Yeah, that's the coefficient of friction we have. It's very small. In other words, as compared to the other metallic bearings where the coefficient of friction could be high in the range of 10 to 30%, this is a much better one. Only thing is, for its fabrication is a problem, because softening temperature is around 375, and fluorine is a very reactive material. Hydrofluoric acid, which forms, is a very reactive material. The container in which you have to keep it is a problem. Anyway, we do have a lot of manufacturing going on for the Teflon these days, and we make use of it. Civil engineers exploit this in push launching of bridges. The girder they make is let us say the span offshore, and the piers are already made in the stream. Over the piers, instead of lifting it with a crane and putting it over the piers, it can simply be slided with the help of jacks, screw jacks, or the hydraulic jacks. The capacity of the hydraulic jack has to be just 1%. If the coefficient of friction is 1%, it has to be only 1%, not the dead weight. If I have to lift it with the crane, the capacity of the crane should be the weight of the span itself, which could be a few tons. Instead of that, 1% of it, I can have hydraulic jacks, and I can simply push it like this over the piers. So pads are made of Teflon, which are put on the piers, over which the steel bits can slide easily, right? That is where the push launching of bridges by the manufacturer, or rather the labor cost and the installation cost becomes very small if you use that. And civil engineers all over the world are exploiting this. Then comes the next, polyacrylonitrile, again a very important material. As a matter of fact, it is a starting material to make the carbon fiber. Carbon fiber is not produced from graphite, but is produced from a polymer like polyacrylonitrile, where this is Teflon, of course, where the four side groups are fluorine. According to polyacrylonitrile, which is a substitute for wool, and we use it as a substitute for wool, this material. This is the side group R1, R2, R3, which are hydrogen. The fourth one is CN. This is nitrogen, this is carbon. This is polyacrylonitrile, to substitute for the wool, and is used as a starting material for making carbon fibers. We have to remove slowly this nitrogen, hydrogen, and make it a chain of carbon. Okay, and ultimately in 3 dimensions will form the sp2 bonds of carbon and form a fiber. Right, these are the plastics, some of the plastics, not all the plastics I have talked about, but the ones which are easy and simple ones to understand. These days we have a lot more plastics, engineering plastics, which we have exploited, and they have provided us good strength in making the engineering components like gears, axles, etc. We can make of these materials. Then we move on to the next kind of a long chain polymer, the fiber. As I said to start with, these are characterized by the linkages which create hydrogen bridges between the chains. That is important. And we shall look at with the help of nylon 6,6. We call it 6,6 because in the backbone of the chain, there are two sets of carbon atoms having 6 each in a group. These two groups have 6 carbon atoms in each group, that's why it is called 6,6, and they are linked with polyamide, and that's what polyamide linkage is. Let's look at that. Well, here is this long chain similarly this one would be oxygen here. I have not shown the side hydrogen groups, 2 of them, which will be there for each one of these carbons, See, nitrogen has 3 bonds, one hydrogen, one with carbon, one with carbon. Oxygen has 2 bonds with this carbon, double bond. Similarly, here this oxygen has double bond. This is my linkage. In the backbone I have 1, 2, 3, 4, 5, 6 carbons, and then another set of 6, 1, 2, 3, another 3 like that. Similarly 1, 2, 3 and so on and so forth. 6 of them will be the next, where this carbon is also counted from the linkage which is there. Now you see this hydrogen here and oxygen here, when they come, hydrogen is just a proton. After it has shared the electron here, it is only a proton, okay, and that proton forms a hydrogen bridge with this oxygen like this, and this will be forming hydrogen bridge here, that will be forming hydrogen bridge there, will also be forming the hydrogen bridge there. So there is a constant interval at which these hydrogen bridges are coming, okay. There is going to be, I think this will have an oxygen here. So these 6 carbon atoms are coming, then the next 6 carbon, and between the 6 there is a link formed, and all the chains get linked like this. It forms a fiber. That's what we understand, that's how all the fibers are made, they are straightens fibers. And this nylon is very strong, and we use it for making ropes, etc. And this is what I have shown is in the form of these balls. These are all carbons, 3, 4, 5, 6. Then I have this nitrogen here, there is a hydrogen bonded to 1 and 1 carbon here, 1 carbon there, and this is carbon which has an oxygen here, double bond. Only 1, 2, 3, 4, 5 and 6, again 1 double bond, and there will be, here there will be nitrogen connected to this, and it will be double bond there, so it will be only nothing, but this will be carbon again, but that carbon will be now bonded to the, should be the nitrogen there somewhere. One double bond, one. This is nitrogen, yeah, that's going to be nitrogen here. Here it will be the nitrogen. So that's how this between every 6 there is a link, and this nitrogen or this hydrogen and the oxygen will form a hydrogen bridge, and that will be coming at the constant intervals everywhere. Same is true with cotton, dacron, terylene, and all these fibers we have. This is all true with all of them. Then third one, we come to the elastomers. Rubber like elasticity they are showing. Structure wise, they have long chain polymers. It's important, though I said they are somewhere between, but basically they should be long chain polymers. However, in the chain there should be a few cross links, and these cross links are at a distance of a few hundred monomers. It's not very close. If I do that in every monomer, it's a network polymer, it is no more a long chain polymer. And that network polymer would never behave like an elastomer. It is behaving like an elastomer because of these conditions which I have listed here. It's a long chain polymer, and there are a few cross links, that is at a distance of a few hundred monomers. Thirdly, the monomer and subsequently this added monomers will form a chain, provide a natural tendency for banding and coiling in the chain. We shall look at with the help of one natural elastomer, which is polyisoprene. There is a natural tendency for banding and coiling. It's essential. And lastly, the chain segments which are there, they must have translational mobility at room temperature if the material has to behave like an elastomer. Otherwise, these conditions can be satisfied for a few degrees by most of the polymers before they melt. That doesn't make them elastomers. If I am the room temperature, when I can use them, room temperature could be 4 degrees centigrade, it could be 44 degrees centigrade in Delhi. As long as it can continue to work like rubber, whether it's a tire of a truck or a tire of a automobile, or it could be the tube, or it could be eraser, or it could be rubber band, I should be able to use it like an elastomer, right? So that's, we shall see all these conditions satisfied first in the case of polyisoprene. It's a naturally found material, polyisoprene. How do we extract it from the tree, rubber plant? It's taken out in the form of the liquid. It's taken out in the form of a liquid. So at room temperature, these chains are flowing, translating with respect to each other. So that condition number 4 is already satisfied. Chains are translating at room temperature, so as it is taken out, it's a liquid. And in this form, I am not able to use it as an elastomer, right? Alright. Then, third point which I said from backwards I am still looking at, there should be natural tendency for banding and coiling. That's what I shall show here. This is CH2 is here, CH is this, and then this is a double bond with carbon which is connected to CH3 which is here, which is rather here, and then connected to carbon, another carbon which has 2 hydrogens, and then again this will be linked. So the one or the next monomer comes here, another monomer comes there, in between this is like this. This requires more space than the hydrogen. There is lot of space in the plane here all around. Around this double bond, if you go around, there is a lot of space. But because it is a double bond, rotation is not possible. So in order to find a space for this bigger side group, this bends about this double bond. Double bond is not straight, double bond bends about this, so that provides enough space for this to be placed. So that provides a natural tendency for it to bend and coil. Because of this one side group which is bigger than the others, it provides tendency for bending and coiling. Though there is enough space here, if I straighten it out, there is a lot of space here, but between this and this hydrogen it has to find a space, and that space is provided by bending. It's been shown by a little more bending. It's not going to be so much of a bend, because after a few means tens or few hundred maybe, I get one coil formed, So this is how the coils are formed. There is a natural tendency for the chain to bend and coil, right? That's the point number 3. Then the point number 2, this is how I get the material from the tree, and it is a liquid. In this form, can we use it as a rubber band? Can we use it as an eraser? Can I use it as a truck tire? No. So we have to provide a few cross links in this, and these are possible to provide because there is a double bond here. If I break this double bond, make it a single bond here, the bonds for this carbon and that carbon, a tetrahedral bond will have to be formed. Both these carbons have one unsatisfied bond once this double bond is saturated, and this is provided by, when this liquid taken out from the tree is to be made useful rubber, what we do is we vulcanize it. Vulcanization process is simply heating this rubber liquid or polyisoprene liquid with sulfur. What sulfur does is, it breaks this double bond and bonds with this carbon and this carbon. But sulfur also needs two bonds. So the second bond of sulfur goes and bonds of somewhere else. It may go to another monomer of another chain. Both of them may go to the same monomer, both of them may not go to the same monomer. They may go to different monomers of different chains. So there is a link which is called the cross link between this chain and another chain. Cross link is formed because of this breaking out the double bond. Two single bonds are formed which are joined by sulfur. That's the role played by sulfur in this during the process of vulcanization. Now it becomes a solid mass which can be used as an elastomer. It is going to be a soft rubber if I do the cross linking 0.5%. It will be a hard rubber if I do a cross linking 5%, 10%. It will be still harder if I do it 20%. But if I do the 100% cross linking, every double bond is broken to form a single bond. This will become a network because this is connected to something else. That in turn will be connected to something else. Like that, the whole thing will become a network. So the two rubbers are very different. After complete networking, after complete this thing, this material is called ebonite. And you know, ebonite is a rigid material. It's not an elastomer. So that's why I said I want the cross links after every few hundred monomers, a few thousand monomers. Softer, few thousand will be very soft rubber. Rubber band, you want it to be soft. There will be less cross linking. Like eraser, a little harder, right? Tire of a truck or an aircraft, you want it to be hard. But the tube inside, you don't want that to be so hard. It's soft. So you have done more cross linking, more vulcanization for the tire and less for the tube. That's what you have done, and that's what it is. You can see that now.
So is sulfur the only element used for vulcanization?
Pardon?
So is sulfur the only element used?
No, not necessarily. I can also provide the cross links with the help of small molecules. Rather than sulfur is acting as one atom, you can consider it as a molecule. I can provide a small chain. So there are a variety of rubbers. I am just giving an example of one.
So which element is there in ebonite?
Ebonite is sulfur. This whole thing will become completely vulcanized. It will become ebonite, right? So that's what it is. And then there are two forms of this material, isoprene. In one case, this CH3 group is coming always on one side of the chain. That's called the cis arrangement or the cis polyisoprene. That is what my rubber is. It can also come in the form of a trans, that in one monomer it is on this side, on the other monomer it is on the other side. Alternately it is coming. It is called the trans polyisoprene. In that situation, it tends to become a straight chain and becomes a rigid material. Then it is no more a bent and coil. It is not. And that material is the trans polyisoprene is, I think they name it gutta percha. It's a rigid kind of a material. But this is rubber when it is in this form, which is the cis form. That's what is my rubber. Well, there are many more kind of things like this, but all of them have different kinds of this. Linkages can be provided by one atom, as I shown with sulfur. It could be provided by some small molecules or small chains of the polymers. That's possible. And there are different kinds of elastomers. They all are like this. So these are the four basic characteristics of the chain kind of a polymer, which will qualify to be called elastomer, or it will behave like an elastomer. Only when it behaves like an elastomer, that I call it rubber, right? I do not otherwise call it rubber. That is very important. If I go back to see this is important, that it is a long chain polymer. It is not a network polymer. These cross links are provided, as I showed, by vulcanization. Then there is a natural tendency for bending and coiling because of the cis arrangement. So the CH3 on the same side, and it's a bigger side group, it's more space, and then the chain segments have translational mobility at room temperature. That's how it comes out in the form of liquid from the tree at room temperature. So all these four conditions are satisfied for it to become an elastomer, right? I think we shall now talk about the mechanical behavior of the elastomer, probably in the next class.